I'd like to introduce you to an approach for solving partially observable Markov decision processes, or POMDPs, using the HTN planner SHOP3 and Monte Carlo tree search. So what does this all mean? What does it mean to solve POMDPs online? First of all, a POMDP is a model of the interaction of an agent with a partially observable environment that has three components. One, a transition relationship, which specifies a distribution over successor states when the agent takes a particular action in a particular state. Two, a reward function, which specifies the cost or benefit of taking an action in a state. And finally, an observation function that specifies a distribution over possible observations when an agent takes an action in a state. Now, as an example, the right side of the slide shows the textbook case of the oil wildcatter. In this POMDP, in the initial state, a stochastic choice determines the state of the oil field, which the wildcatter does not observe. Then the wildcatter can choose whether or not to make a seismic test. If they do so, they'll make an observation that's a stochastic function of the oil field state. So we'll give information about the likely oil field state. After testing or not, the wildcatter chooses whether or not to drill. If they drill, they incur a further cost and receive a reward that's a function of the oil field state. So what does it mean to solve a POMDP? There are several different definitions of solving a POMDP, but typically we mean choosing a series of actions that will maximize the agent's expected reward. This is often done by computing a policy, which is equivalent to a conditional plan or a closed loop control program or an optimal strategy in a two-player game. Okay, what do we mean by solving a POMDP online? When we solve a POMDP online, we choose the action when we need it rather than computing a program that dictates how to choose an action in every possible state, a policy. This can be more efficient because policies can be exponentially large. Solving a POMDP online is very much like playing a two-player game, except the opponent is nature instead of another person or a computer. In order to solve POMDPs online, we've integrated Monte Carlo tree search into SHOP3. Monte Carlo tree search is a search algorithm that was developed for games with very large search spaces, such as Go. One way to think about MCTS is as a fusion of reinforcement learning and search. MCTS chooses search actions balancing exploration, looking at new parts of the space, against exploitation, further exploring promising parts of the search space in what's called its tree policy. And then it uses a cheap default policy to extend its rollouts all the way to a terminal state. It then backpropagates the result from the terminal state, so its benefit or reward or cost, all the way back up the tree and repeats. When it's exhausted its resources, it chooses the move that looks most promising given the set of rollouts so far, receives a move from the environment, and starts over. To solve POMDPs, we've extended SHOP3 to represent POMDPs and have incorporated MCTS into SHOP3. The two distinctive features of the SHOP family of HTN planners that are most relevant here are first, that it's a forward planner. So at every stage of the search, it has a fully fleshed out world state. And two, it permits its preconditions to use external code. Based on this, we can capture POMDPs with modest extensions. First, we add a hidden modality to the state to indicate unobserved state literals. And second, we model uncontrolled outcomes as method choice governed by preconditions using the random function. In this way, the standard SHOP planning algorithm can compute a single trace through a POMDP. To implement MCTS for POMDPs in SHOP, We run shop over and over, making the agent's method choices based on a tree policy. One subtlety is that because there is only partial observability, the agent cannot choose its action based on hidden information, only visible information. So our system must choose actions and propagate using sets of states equivalent with respect to observed history while projecting based on full states. So that's a quick introduction to our new system, Shopping Spree. It's a full implementation of the method, but the implementation is still rickety. We will make it freely available when it is complete. Right now, it works only for plan libraries that satisfy a particular interruptibility property we can discuss at the poster session. We are working right now to address this through incorporating plan repair, and we're also working to make the system more solid and faster and apply it to experiment planning problems. I look forward to discussing this further at the poster session. Thank you.